Hello everyone, welcome to my talk called Select Code Execution from Just About Anything Using SQLite, where we will gain code execution using malicious SQLite databases. So, quick who am I? My name is Omer Gull. I'm a vulnerability researcher from Tel Aviv. I've been working in checkpoint research for the past 3 years. This is where I've done this research, and I've recently moved on to a new startup called Hunters AI. So, the agenda for today will start with a little motivation and the backstory for this research. We'll then talk a little bit about SQLite internals. We will examine the attack surface available to a malicious database and discuss some previous work done in the field of SQLite exploitation. We will then move on to memory corruptions and the possibility of exploiting them using nothing but SQL queries, and demonstrate our innovative technique called query-oriented programming, or COP. That's a registered trademark. We'll take it for a spin in a couple of demos and discuss some possible future work and conclusion. So, let's get started. The motivation for this research is quite obvious. SQLite is one of the most deployed pieces of software in the world. Whether it's PHP 5, 7, Android, iOS, macOS, it is now built into Windows 10. It is practically everywhere. Yet, querying a database is considered safe. And hopefully, by the end of this talk, you will realize why this is not necessarily the case. So, it all actually started with password stealers, and it's a pretty popular type of malware. And there are several types in this field, but the story is usually all the same. First of all, a computer gets infected. Then the malware collects the stored credentials as they are maintained by various clients. Some of these clients actually store your secrets within SQLite databases. So the malwares just ship those databases to its C2 server, where they are all parsed, and your secrets are stored in a collective database with the rest of the loot. So it all actually began when my colleague and I, Omer, we were looking at the leaked sources of a very known password stealer. And then we thought to ourselves, these guys are just harvesting a bunch of RDBs and parse them in their own backend. Can we actually leverage the load and query of an untrusted database to our advantage? If we could, this might actually have much bigger implications just because SQLite is so popular and used in countless scenarios. And so began the longest CTF challenge of my life. So, a couple of words about SQLite. So, unlike most database engines, it doesn't have the client-server architecture. Instead, it just reads and writes directly to the file system to files. So you have a complete database with multiple tables and indices and triggers and views, and everything is contained within a single file. So let's examine for a second the attack surface available to a malicious database. Again, this is the leaked sources of a very known password stealer, and we have two main points of interest here. The first one is SQLite Open, where our potentially malicious database is about to be loaded and initially parsed. And the second point is obviously the query itself. Now, do notice that this query is uncontrollable to us, right? It is hard-coded within our target. Yet we have some control over the database, so it should be beneficial to us to learn this process. So let's break the attack surface in two. First of all, the SQLite Open. So actually, it's a bunch of setup and configuration codes, a bunch of modules are loaded, and then we move on to straightforward header parsing. And actually, the header is not that long; it's only 100 bytes long, and it was already fuzzed to death by AFL. So probably this is not a very promising path to pursue. The second part of our surface, the query itself, and it might be a bit more interesting because using SQLite author's words, the select statement is the most complicated command in the SQL language. And actually, SQLite is a wonderful virtual machine. So every query is first compiled to some bytecode. And this is also known as the preparation step. So SQLite Prepare would actually walk and expand your query. So for example, every time you write an asterisk, it goes and behind your back replace this asterisk with all the column names. So SQLite locate table actually verifies that all the relevant objects do exist and locates them in memory. So where does this object exist? Every SQLite database has an SQLite master table that defines the schema for the database. And this is its structure. You can see that it's actually a table, and every entry there has the type of the object, so like a table or a view, and its name and root page, because if you recall, everything is contained within this file, and a field called SQL. And SQL is actually the DDL describing the object. So DDL stands for Data Definition Language, and you can sort of look at it like your header files in C. So they are used to define the structures and the names and the types that are used within the database. Furthermore, they also appear in plain text within the file. So let me show you an example. Here I create a very simple database. I create a table and then I insert a couple of strings into it. Then I quit the SQLite interpreter and I hex dump the file. And you can actually see the DDL in text, the DDL of SQLite master, in plain text within this file. So let's go back to query preparation for a second. So we have SQLite locate table that attempts to find the structures describing the table that we are interested in querying. So it reads the available in SQLite master. And if it's the first time that it's doing so, it has a callback function for every DDL statement. This callback actually validates that the DDL is indeed valid, and it builds the internal data structures of the object. So then we thought about what about DDL patching? Can we simply replace the SQL query within the DDL? And turns out that this is the callback function that I mentioned, and you see that the DDL is verified to begin with create space, and only then it moves on to preparation. So that's actually a constraint. Our DDL must begin with create. However, it does leave some room for flexibility, because to judge by the documentation, actually many things can be created in SQLite. So you can create an index and a table and a trigger and a view, and something we still don't understand called virtual table. And then create a view gave us an interesting idea, because views are simply prepackaged select statements, right? And they are queried similarly to a table. So selecting a column from a table is semantically equivalent to selecting a column from a view, right? So we move on to the concept of query hijacking. We are going to patch SQLite master DDL with a view instead of a table. And our patched view can actually have any select that we wish. And now using our select subquery, we can actually interact with the SQLite interpreter. And this is a huge step forward, right? Because the query was uncontrollable by us at first, so now we have some control over it. Let me show you an example. So let's say that the original database had just a single table, and it's called dummy, and it has 2 columns inside it. The target software would actually query it the following way. It would just select those 2 columns out of the table, right? But the following view can actually hijack this query. So if we create a view that it's called dummy, it has the exact number of columns inside and the same name, and every column can have any subquery that we wish inside it. So again, let me show you a practical example. Here I create a database, and inside it I create a view with 2 columns. Every column is actually a function. So the first column would call the SQLite version function that simply returns the SQLite version in use. And the second column will utilize SQLite's own implementation of printf. That's right, they have their own implementation of printf. They must be insane. So now when the target software actually queries what it thinks to be a table but is actually a view, we can actually see our 2 functions executing. And again, we just gained some control over the query, and this is a huge step forward. But then the question is, what do we do with this control? What primitives does SQLite have? Do we have any system commands? Can we write to other files on the system, maybe read some more files? So this is a really good point to look back at previous research done in the field, because we are definitely not the first one to notice SQLite's huge potential in terms of exploitation, right? So a reasonable place to start is SQL injections, right? And there are a couple of known SQL injection tricks in SQLite. The first one has something to do with attaching another database and creating a table and then inserting a string into it. So you are able to write your own web shell, and this is all very nice, but we can't do it because if you recall, we can't start any statement with attach. Our DDL must begin with create, so it's not a very useful trick for us. Another common thing to do in SQL injection is loading a remote extension. Like here in this example, you can see it actually loads the Meterpreter DLL. However, it is also disabled by default, so again, no go with this trick. Let's talk about memory corruptions for a second, because SQLite is such a complex piece of software and everything is written in C. So in his amazing blog post, Finding Bugs in SQLite the Easy Way, Michael Zalewski, the author of AFL, described how he found 22 bugs in just under 30 minutes of fuzzing. And this is pretty amazing. And interestingly, since then, that was version 3.8.10, that was 2015, SQLite actually started using AFL as part of their remarkable test suite. Yet these memory corruption all proved to be really difficult to exploit without a convenient environment, right? But the security research community soon found the perfect target, and it was WebSQL. So WebSQL is essentially a web page API for storing data in databases. It is queried from JavaScript using SQL, and it has an SQLite backend, and it is available in Chrome and Safari. Here we see an example of how to query SQL to SQLite using JavaScript. It's very straightforward. But in other words, what I'm hearing here is that we have untrusted inputs into SQLite, available, reachable from any website on the internet in two of the world's most popular browsers. And now every memory corruption bug could actually be leveraged with the comfort and knowledge of JavaScript exploitation. So there have been several impressive researchers that were published about WebSQL. From very low-hanging fruits like CV 2015-7036, that was an untrusted pointer dereference in FTS tokenizer, to more complex exploit presented in Black Hat 2017 by the awesome Chai Tin team, that was a type confusion in the FTS optimizer, to the recent Magellan bugs that were just presented by the Tencent team, that was an integer overflow in FTS segment reader. And if you guys are paying even a tiny bit of attention here, you might see an interesting pattern arises, right? All these functions starts with FTS. So what is FTS? I've never heard of it, and Googling it just even left me more confused. Well, after some time, I came to the realization that FTS actually stands for full text search, and it is something called a virtual table module. And it allows for textual searches on a set of documents. Again, using SQLite author's words, it's just like Google for your SQLite database. So that's pretty cool. And a virtual table actually allows for plenty of cool functionality in SQLite. So we have FTS that we just described. There is also R-tree, a virtual table that allows for some clever geographical indexing, or the CSV virtual table that lets you treat your database as you would a CSV file. And actually, all these virtual tables are queried just like regular tables. But behind the scenes, some dark magic happens, because every query invokes a callback method on something called shadow tables. So, shadow tables. For example, let's look at a virtual table that is created using FTS virtual table module, right? So we create a table, and we insert a string into it. Now, obviously, to allow for some efficient search, we need to have some metadata, right? We need to have some indexing or pointers or some tokens or stuff like that. So obviously, we have the raw text and some metadata. But this one virtual table is actually comprised from 3 shadow tables. So the raw text would go to a shadow table called content, and the metadata would go to the segdir and segments. And actually, each of these shadow tables, they pass information between them. They have all those interfaces. And those interfaces, given that they have such trusting nature, they are really fertile ground for bugs. Many of the bugs in SQLite are presented there. So it's a really good thing to look at if you're hunting for bugs. And let me show you an example of a bug that I found in one of the interfaces of the R-tree virtual table. So again, R-tree is a virtual table module, and it is available in macOS and iOS, and now also built into Windows 10. And it's used for some geographical indexing. I'm not entirely sure what that means, but the structure should be the following. A table should begin with ID, that is supposedly an integer, and then you have a bunch of coordinates, like x and y's. So R-tree interfaces would obviously expect ID to be an integer. But if we create a virtual table using the R-tree module, and we'll insert a value where ID is definitely not an integer, but it's a string, and then we use the R-tree node, that is one of the R-tree interfaces, we get the following CVE. That's an out-of-bound read, and it's really cool because this bug is now available in iOS and macOS, and as you can see here, also in Windows 10. So let's go back to exploitability for a second. We realize that virtual tables do have bugs, right? And using our method of query hijacking, we can actually trigger them at the C2 and cause it to segfault. But gaining flow control requires some form of scripting, right? Because segfaulting is not enough. We want to write a complete exploit. We want to bypass ASLR. We want to have some logic. However, we don't have the JavaScript interpreter, so we don't have any variables or arrays to use like you would in web SQL exploitation. However, we do vaguely recall hearing somewhere that SQL is Turing complete. So we decided to put it to the test in terms of exploitation. And we started writing our own wish list for exploitation primitives. So obviously we'll need to leak some memories, right? We want to bypass ASLR. We'll have to do some common tasks like unpacking 64-bit pointers to integers, and then do some arithmetics with them, right? We want to calculate where functions are or where the heap is located. Afterwards, we want to pack those integers back to little endian 64-bit pointers, and maybe we also want to fake some objects in memories. This is a really powerful primitive that is really helpful in many vulnerabilities. And we want to know how to heap spray, because why not? It might be really, really useful. So the question remains, can all these primitives be achieved with nothing but SQL? And the question is, yes, it is. So I proudly present to you something we call query-oriented programming. And to explain it, we will exploit the unfixed CVE 2015-7036. And you might ask yourself, how come a 4-year-old bug is still unfixed? But this is exactly our point. It was only considered vulnerable from the context of the untrusted web SQL. So it was mitigated accordingly. It's just not available in web SQL anymore. However, so it is blacklisted actually unless you compile SQLite with a certain flag. But these platforms are still vulnerable. So we have PHP 5 and PHP 7 and iOS and macOS all still vulnerable to this CVE. So let's describe the vulnerability a little bit. So we said that it has something to do with the tokenizer. So a tokenizer is a set of rules for extracting terms from a document or a query. And the default is called simple, just split those strings by white spaces. However, if you like, you can register custom tokenizer using the FTS tokenizer function in an SQL query. I will repeat it slowly. You can actually register a function using an SQL query. You are about to pass a raw pointer to an SQL query. This is absolutely insane. Actually, I have no idea how to really use this functionality other than in my exploit. So, FTS tokenizer is actually an overloaded function, and if you call it with one argument, so simple, again this is the name of the default tokenizer, it actually spits back the address of this tokenizer. So to make it a bit more readable, we'll use the hex decoder, and we can see that we actually got a pointer to lib.SQLite, but it's the other way around because little endianity. And if you call it with two arguments, so the first one is the tokenizer name, the other one is a raw pointer, you actually override the address of this tokenizer. So everyone trying to use this tokenizer, everyone instantiating a virtual table, will try to initialize it and will then crash and burn with segmentation fault at the address given to it. So a little recap. We established that SQLite is a wonderful one-shot for many targets. One good bug in SQLite is one good bug in so many platforms. And we realized that it is a complex machine written in C, and using query hijacking, we can now actually start triggering bugs. And we aim to write a full exploit, implementing all necessary exploitation primitives with nothing but SQL queries. So, our exploitation game plan is as follows. We are going to leak some pointers, and then we'll calculate some function addresses. We will create our own fake tokenizer with some pointers to system to allow us to actually execute code. We will override the default tokenizer and trigger it, right? And then something will happen, and I know what you think is going to come up next. But we are not going to profit. We are going to grab your grandma's Yahoo password because this is what is available in password stealers. So, starting with the memory leak. First of all, we need to gain a leak to lib.SQLite, right? So we already know how to do it, right? The FTS tokenizer just give us the address. But we have a slight problem because it's in little endian, so we need to flip it. So surely we can read the pointer in a reverse fashion, 2 characters at a time, and concatenate everything together. So our leak would eventually be the following query, and we actually now have a leak to lib.SQLite. This is really, really cool. Another thing that is going to be useful for us is a leak to the heap, right? So I'm going to do something pretty similar to the archery bugs that I've shown you. I'm going to confuse a virtual table interface. So again, I'm creating a virtual table, and I'm inserting a string into it, and then I will confuse the match interface that is usually passing a pointer, but instead of passing it to some other interface that is expecting this pointer, I will simply pass it to the hex decoder again. So now we read this pointer, and it is indeed a pointer to the heap, again in little endian, but using the trick above, we should be fine in flipping it. So we can cross that off the list. We know how to leak memories. Now it's time to unpack some pointers. But before we do that, we actually have a slight problem, because unlike browser WebSQL exploitation, we don't have any JavaScript variables or arrays to use. And this is a big problem because we need to create some logic. We want to calculate things. We want to store things. And naturally, storing things in SQLite requires you to have some insert. But we can't use insert, right? We have to begin with create. And we can only create tables and views and indexes and triggers. So then we thought about chaining a couple of views together and use them sort of as pseudo variables. Again, let me show you an example. We create a view called little endian leak, and we use the vulnerability as mentioned in the earlier slide. Now we create another view, leak, and notice how it refers to the first view, right? It's selecting from little endian leak. Again, we are doing the trick from before. And now we actually remain with a pseudo variable called leak that is actually all these chains together. So we have one pseudo variable that contains all the calculations from before. And again, this is a huge step forward because we want to create some logic. Our exploit should bypass ASLR and those kind of things. We need to be able to store things, and this would really help us. So, unpacking 64-bit pointers. To calculate the base of an image or the heap, we have to convert our pointers to integers. And this can be done using the following query. So again, we start with substr, reading one character in a reverse fashion. Then we take this character and we use it in str. In str is just like strchar. And we get the value of this hex character. Because it is one based, you have the -1 on the side. And then you have some multiplication and shifting dark voodoo. And you simply return it for every character in the pointer, resulting in this monster query. But eventually, we actually unpacked the pointer, and now we have the integer value. So, again, we can cross that off the list as well. Moving to pointer arithmetics, and it is actually really, really easy right now when we have integers at hand, right? All we have to do is, in one subquery, we use our pseudo variables, and the other one can have any constant that we wish. And now we know where lib.SQLite is located. So, packing 64-bit pointers, because we read some pointers and we manipulated them, now would be a good time to write them somewhere. So we thought char is going to be really useful here because we are used to char being the reverse of hex, right? And it actually works fairly well on some values. But on higher values, this was a problem because they were translated back to their 2-byte code points in Unicode. And this was a huge obstacle for us. And we actually had a really big problem with this. And after bashing our head against the documentation for about a week, we suddenly had the strangest epiphany that our exploit is actually a database. And if I want any conversion to happen at all, I can simply prepare a key value table in advance while I'm generating this database and then use some subqueries. So this is the Python function that is actually generating this hex map key value table. And you can see that it's a very simple for loop from 0 to FF, just inserting all the values that I wish. And now our conversion use subqueries that are selecting from this hex map. So you see how the view is referring to hex map. And again, we have some shifting and modulo dark magic, and we concatenate everything together, resulting in this query. So now we also know how to pack 64-bit pointers. We are moving forward. Let's talk about faking objects in memory, because writing a single pointer is definitely useful, but it's not enough, right? We all want to fake objects in memory. It's a really powerful primitive. And if you recall, FTS tokenizer actually requires us to assign a tokenizer module, so we need to fake one. And a tokenizer module is the following struct. We don't really care about most of it. It starts with an integer, and then it has 3 function pointer. First of all, we have the create, which is the constructor. Then we have the destroy, which is the destructor. Obviously, we want both of them to be valid because we don't want to crash during our exploitation. The third function pointer, open, actually tokenizes a string. So it gets a string as an argument. This would be a really good place to put our system function so we can execute code as we wish. So I've used most of my SQL knowledge by now, but I still have one more trick up my sleeve. I remember join queries. So we are going to fake an object using the following join query, right? We can see that we created a view called fake tokenizer, and it's concatenating a bunch of A's and then a packed version of the simple create address and then another packed pointer and then a bunch of B's with a join query. So actually, if we verify it from a debugger, we can actually see that it works pretty good. The memory section begins with a bunch of A's, and then we have 2 pointers, and then we have a bunch of B's. So we have successfully faked an object in memory using nothing but SQL queries so far. So for our final primitive, we want to do some heap spray. Because now we have our malicious tokenizer, right? And using our leaks, we also know where the heap is, but we are not entirely sure where our tokenizer is inside the heap. So it's time for some spraying. And ideally, that would be some repetitive form of our fake object primitive, right? So repeat sounded like a really good option to us. Sadly, SQLite did not implement it for us, so we had to do it by ourselves. Stack Overflow for the win. We found this really elegant solution. So the following query, it uses the zero blob function that returns a blob consisting of n bytes. They're all zeros, right? And then we'll use the replace function. We're going to replace each and every of those null bytes with our fake tokenizer. So again, the colors here are pretty bad, but verifying it with PondDBG, we actually see that we got perfect consistency. Our fake tokenizer is repeating itself every 20 bytes, so this is perfect. And it looks like Christmas came early because we can go on to pawning shit. So again, our target is the following code, right? We have the password stealer, and it selects a column called bodyrich from a table called notes, right? So we are going to create a view that is called notes, and it will have 3 subqueries inside. We're going to start with a subquery called heap spray, and then we'll override the simple tokenizer, and then we'll trigger our malicious tokenizer. And you might ask yourself, what is a heap spray? Well, heap spray is obviously a cop chain. It's another view called heap spray that utilizes our heap spray crazy capabilities. We start with a bunch of A's, and then we concatenate one of the pointers that we are interested in. P64 simple create, for example. Needless to say that P64 simple create is another view, right? That actually refers, it's a packed version of U64 simple create. The party goes on because U64 simple create actually goes back to U64 lib.SQLite that utilizes some of our pointer arithmetics capabilities, right? And everything is derived from our initial leak, the U64 leak. But it's actually turtles all the way down. U64 leak refers to leak, right? And our unpacking capabilities. And leak goes all the way back to our initial vulnerability. And every time I describe this cop chain, this is how I must look, right? I must look insane. But luckily for you guys, you don't have to look like me, because we created cop.py. And cop.py is a really useful Python library for generating these crazy long statements, right? In something in like the style of pawn tools. So creating the pass chain is actually only this like 4 lines of Python. And it's going to be available in our GitHub right after this presentation. So now that we have everything in order, let's show our first demo for today, where we will own a password stealer backend that is running the latest PHP 7. So this is our module. This is our panel. Obviously, it's just a model that we set up from the leaked sources, and you can see all those victims that are infected. And we are trying to go to p.php, where our web shell should be. Obviously, it's still not there because we have yet to exploit it. Moving on to the attacker's computer, we see that we have 2 scripts. The first, cop.py, will actually generate our malicious database. And we see, using ls, that a database was indeed created. Now we are going to emulate an infection, right? So we are going to send this SQLite database to the C2 server as if we were infected, and it has a bunch of password that is interested in. And this process takes a bit of time, so we can look at all the crazy statements above. We started with the leaks, and then we unpacked them and packed them again and manipulated. And you see that at the bottom, our payload is actually creating p.php with the simplest web shell. So after our exploit will run successfully, we'll go to that page. Now that it's finished, we go to p.php again, and we see we got 200, the page to exist. So now we can actually execute some code on the backend. Who am I? www.data, and obviously cutting etc password, and we got it. Yeah. So actually, if you think of it, what we just demonstrated is that anyone querying our malicious database can actually be exploited, and this is a lot of fun. And given the fact that SQLite is so popular, it opens up the door to a wide range of attacks. Let's explore another really interesting use case. So this is iOS persistency. iOS uses SQLite extensively. It is everywhere, right? And persistency is really hard to achieve on iOS because all executable files must be signed. SQLite database, being data only, are not signed, right? There's no need to sign them. And iOS and macOS are both compiled with the enable FTS tokenizer compile time flag. So we plan on regaining code execution after the reboot by replacing any SQLite DB, right? So as our target, we chose the contacts DB. So this is the name of the contacts. It's address book SQLite DB. And these are a couple of tables inside it. There's nothing really special about those tables. They're just here as an example. We will replace the DB with our malicious DB, right? That will start with 2 DDL statements, and you guys are already familiar with them. The first one will override the simple tokenizer with a bunch of A's. The second one will actually trigger it, right? It will start an FTS virtual table, try to construct our malicious tokenizer. And now what we're going to do is that we're going to go over each and every of the original tables, and using query hijacking, we are going to rewrite them as views, redirecting the execution to our malicious DDL statements. So you see we select from override, and then we select from crash. And then we go and we do it for the second table as well. And we reboot, and secure boot was actually bypassed, and we got the following CVE. And this is really interesting because you can see that the crashing address is 41, 41, 41, 49, and this is exactly as we expected, right? This is where the constructor xcreate should be. But that's actually not everything, because the contacts DB within your iPhone is actually used and shared by many, many different processes. So whether it's the Contacts app or FaceTime, Springboard, WhatsApp, Telegram, XPC, Proxy, many, many processes, some of them are more privileged than others. And we've actually established the fact that we can execute code on the querying process. So this actually means that we got privilege escalation using our tricks, right? And actually there's nothing special about Contacts DB. Any shared database can be used to achieve our goals. All these methods and techniques were reported to Apple, and they gained those CVEs if you want to go and read about it later. So, if you'll take anything away from this research, I don't want it to be the crazy SQL gymnastics, or I don't want it to be a bunch of CVE number. I want it to be the following. Querying a database might not be safe. Whether if it's across reboots or shared between processes or shared between users, querying a database might not be safe. And with COP, actually these memory corruption can now be reliably exploited using nothing but SQL. And we really think that this is just the tip of the iceberg. So far, SQLite was only examined through the very narrow lens of WebSQL. And while browser pawning is really exciting, SQLite has so much more potential from exploitation perspective. So we really want to see where the community will take this research to. And we do have a couple of ideas of our own. So obviously, something really cool to do in future work would be to expand our primitives and gain something powerful as absolute read or write. And second, our exploit was actually a really sketchy POC, right? It had a bunch of hard-coded constants inside. But you can actually make it really, really clever, because if you think that your exploit is actually a database, you can choose the right cop chain for you based on the results of functions like SQLite version or compile option, like getting the compile option used. So you can dynamically create your cop chain to be exact to the target that you are exploiting. Obviously, we think that these techniques can be used to privilege escalate almost everything. All we have to do is find a database that is writable by a weak user and queried by a more powerful user. So it's also interesting to look at other platforms than iOS or macOS. And another thing that is really interesting is that many of the primitives that we have shown are not exclusive to SQLite. You can actually port many of them, like the packing and unpacking. You can port them to other database engines. So this would be also a really cool path to pursue, to see how these techniques work in other database engines. And that's it. Thank you so much.